Good evening, everyone. Thank you for being present for this session. I am Rohan Farat, a PhD student from Indian Institute of Technology, Delhi. So today I will be presenting on the topic Safe Reinforcement Learning Based Vibration Control Overcoming Training Risks with LQR Guidance, which is jointly worked with Juvi Singh under the guidance of Professor Rajiv Naik. So the title seems to be quite lengthy. So first, let's me briefly explain it. Vibration control has long and well-established history, in which there are quite various approaches which are developed over years. Recently, reinforcement learning has been quite useful, especially we have seen that it has been useful to improve the performance of ChatGPT, which now also seems to be useful in the case of vibration control. But from a practical perspective, there is a critical issue. During its training of the controller, it may damage the dynamic system. So in this presentation, I am going to highlight the critical issue and provide a framework in which we can train the controller of RL in a safer way. Large structures such as bridge, building, experience vibrations because of external wind and or earthquake. It is important that we minimize this vibration, not just because it is discomfort to the people around it, but also to prevent damage in it, to reduce maintenance cost, or in extreme cases to avoid hazardous situation. Usually, it can be done using active control. Why? Because it is possible to do so for existing structure, which is not possible for the case of passive control. To do so, in active control, there are popular methods such as linear quadratic regulator (LQR), which is useful when the dynamic system is considered to be linear. When the dynamic system is not considered to be linear, then MPC could be used, which is model predictive control. But there is one catch. These methods are highly dependent on the model of it. To know the model, we need to do system identification, which is time taking, expensive, and usually the model which we get is not accurate. Why? Because the true model only God knows. When we start with this inaccurate model and when we design the control policy, the performance of the controller would not be optimal. So it makes sense that we need to find a way in which we should be able to avoid the need to know the model itself. This is where model free reinforcement learning come into picture. Here, the agent, which is the controller, RL controller, directly learns by interacting with the environment, that is the structure, by giving some action based on some observation from the structure. For a corresponding action, the environment gives some reward to the agent. In our case, our aim is to reduce the vibration. So the reward would be the function of terms which are related to vibration, such as displacement, velocity, or acceleration. Based on the response, that is reward, the agent's, that is RL controller parameter would be optimized. In this iterative way, it learns optimal control. At least in theory, it seems to be nice. During its training, as the RL controller do not have any prior knowledge, it starts from scratch. As a result, it explores. It gives random action, that is random force, and based on the response, it learns. As a result, it may happen that it might damage the system, as seen in the plot. This plot is of the accelerated response during training of RL controller, where we could see that in the blue color it is of the RL controller, whereas in the red color it is of the uncontrolled scenario. It seems to be quite strange that RL controller, because of RL controller, the response of the dynamic system has got increased as compared to that of uncontrolled scenario in training phase. So in some way, we need to be able to provide some prior information, prior knowledge to this RL controller. To do so, we started with one thought. What if the LQR, which is actually a model-based method, what if we design that method without doing system identification? Instead, we designed it based on some random system. What could happen? The first thought would come in our mind that it would destroy the system. Whereas the second, which is the least possible, is it could protect the dynamic system. It could reduce the vibration. To check out what would happen, we took one simple example. We took on a true nonlinear single degree of freedom system. where the external disturbance is ground excitation. Whereas we randomly assume the linear system as shown here. We could see that the parameter values are quite different than the true system, as it is randomly, the parameter values are randomly taken. Now we designed the LQR policy based on this assumed linear system, and we saw the result. The result seems to be quite satisfactory. We could see that as compared to the uncontrolled scenario that is shown in the blue line, the LQR, which is designed based on the complete random system, it is able to minimize the vibration in the case of displacement velocity and acceleration. Why? Why did that happen? Because the system, true and assume, they are different in terms of its quantitative characteristics, but it is same in terms of qualitative characteristics. The spring mass damper system, the both the case, true or whether it is assumed, it opposes the direction of displacement. That is why this knowledge is also useful. It could also be useful if we use for a RL case. With this observation, we made one LQR guided RL framework. Here, we took the policy, LQR policy, which was designed based on assumed random system. We took it as shown in light blue color, which is represented by F5. Then, depending on our how importance we should give to the prior knowledge, we multiplied with alpha, which range from 0 to 1, and the remaining value which need to be added to it, so that we get an optimal policy, is learned by our RL controller, that is represented by F theta. Using this framework, we have shown the result from the training phase. Here, the acceleration results are shown where in blue it is of the RL controller, and in red it is of LQR guided RL. We could see that the prior knowledge has been helpful. The vibration has reduced quite well. Using the same approach, we saw how it worked in testing phase. Here in testing phase, especially the acceleration. Acceleration is the parameter which makes us feel discomfortable. Especially in acceleration parameter, we could see that as compared to LQR, which is represented by blue color, LQR guided RL perform well. Along with this vibration, we also look into the factor that how much energy our controller consumes. So to look at it, we look at the control force. Also in the control force, LQR guided RL perform well. This is the overview of the training algorithm of the RL controller. Starting from the top left hand side, from the first, where we randomly we design the LQR policy based on the randomly assumed system. Then we initialize the RL networks which need to be trained. Then secondly, we start the training of the controller. Thirdly, we add the value which we get from LQR controller and the RL controller. Then we give as an output to the fourth in the environment, that is structure. Then we observe the responses from the structure and we store in the fifth step. Based on the responses, we update the neural network parameter of the RL controller. This iteratively goes on till we get our converged solution. And in the last 7 step, we obtain the optimized parameter. So to summarize, we highlighted the key issue that it works fine, the RL controller works fine in simulation, but in from a practical perspective, it may fail. Secondly, we show that LQR controller, if designed on a randomly assumed system, still it gives some useful information. Thirdly, we show that we could not only it helps in our training phase to minimize the vibration, but also it works fine in the testing phase. And last, instead of using LQR, which is used usually in a model-based framework, we are able to pose it as a model-free approach. Here we as we are taking the LQR based on the random system, which is not in our hand. So the values of the random system as far they are from the true system, the prior usefulness of the prior knowledge will get reduced. Second, we have tried it only on single DF, so we can't comment much how it would scale. Thirdly, the sensor noise are not considered in this work. Then usually there are delay in the actuator, which is not considered in this work. For a future work, it would be good to see how it works in multi-DF Secondly, there is need to do experimental work, and lastly, there is one other way how we could tackle the same problem to make it safer. Thank you.
A question answer if someone has.
Nice presentation. Can you explain how it works in practical scenario? If I have a building, a two-story building, there is an earthquake of magnitude 5. Then how is it? Is it a model?
In practical, there is some called as actuator, which I place force.
Actuator, okay.
So yes, so there would be some few sensors placed on the
actuator
structure, and also if anyone want to know the earthquake excitation on the ground itself, so based on that observation, the actuator would put force,
okay,
in a particular direction.
Okay. So I just want to know how it is controlling the vibration of the building, or what?
It is trying to, yes, it is trying to minimize the vibration of the building. It is controlling.
How it is minimizing?
For
I
example,
am not from this area.
yes, for example, let's say if we think of a single degree of freedom spring mass time system, if the mass is moving to right from neutral axis, then if we apply the force toward left, then it would minimize the vibrations in the same way.
So it is giving a opposite inertia.
Yes, opposite force. Yes, opposite inertia.
So basically, it is making the equation static, quasi-static.
Static. It is trying to take this equation to static.
Minimizing the inertia.
Yes, yes, correct. This inertia.
Any other question?